we've got shallow neural networks versus deep neural networks. And so where I'm going with this is a way of getting the power of a deep neural network by using a shallow network. So neural network, you just have some inputs. That could be, features that you extract from a legal case. It could be medical data. And then you're going to have some outputs that you want to get from it. And the learning problem is to say, well, if each of these little units here can compute some function of all the inputs, and then the outputs can compute some function of the middle layer, how do I sort of figure out the function that's being computed? So it turns out that it's sort of like a little 3-layer neural network like that is a universal function approximator, meaning it can approximate any computable function arbitrarily well. But the issue is that to do that, you might need lots and lots and lots of those yellow nodes. So many that it's going to be impossible to train. So the trick with deep learning was, well, instead of making this thing wide, let's use sort of not quite so wide, sort of intermediate computations, but stack them and nest them. And what happened was that once we, got a handle on lots of compute, lots of data, and a few clever algorithms, it turns out deep learning is just the way to go, almost invariably. And so here's a couple of networks. There's an old one called a VGG19, which has 19 of those intermediate layers. There's this ResNet, which has 34 of those intermediate layers. There's a ResNet 152, which has 152 of those intermediate layers. And they all tend to be sort of fairly narrow. But the problem is that, there's no free lunch. And so with depth often comes challenges in computation. So, GPT-4 was estimated to have about 1.8 trillion parameters that had to be tuned with data. And so building these kind of domain-specific models starts looking like it's impossible for, mere mortals to do. You have to be one of the top 5 companies in the world to do it. So then came along this paper, which is less is more, recursive reasoning with tiny networks. And essentially what they showed was you can beat general purpose language models at some very hard tasks using a tiny, tiny fraction of the sort of compute that you would have to use otherwise. And so what I want to do is here's a slide. It's got some notation on it, but I'm hoping it'll be super clear. So give me just a minute to talk through it. So think about, we've got 3 things. And so you're solving a Sudoku puzzle. Let's use that as an example. So everybody's played Sudoku, where you've got some numbers in these grids and you've got to fill in the rest of the numbers, and there's certain constraints on it. So suppose if I give you a Sudoku puzzle, which is an X, right? So I'm going to give you an input. Here's the problem you're going to solve. What you're going to do is you're going to spend some time kind of thinking about it. So you'll have sort of thoughts and this is how I think I'm going to attack this part of the puzzle. We're going to call that thing Z. And then eventually you're going to produce an answer, which is Y. So you're going to get input, you're going to think for a while, then you're going to produce an answer. And so what this paper does is it goes, all right, let's have one tiny little 2-layer network. It's not deep. It's just this little, we get inputs and the thinking part, which is the Z, and then the outputs. And that thing says, all right, well, if you tell me what your problem is, what your current thinking is, and what your current answer is, I'll help you refine your thinking, right? Okay, here's some other things you should consider. And then when you're done thinking, you can say, here's the input, here's my thinking. I'm not going to provide you with an answer. You tell me what the answer to the problem is, right? So the way the method works is you just say, I don't know what the answer is. I don't really know what I'm thinking. I'm going to randomly initialize those. And so you go, all right, here's the problem. I got some random answer and some random thoughts. Give me better thoughts, right? How should I refine my thinking about the problem? And then you say, okay, given the input in my refined thinking, what should the answer be? And then in a standard sort of learning paradigm, you just update the model based on the ground truth. But the sort of novel thing here is that this happens in a loop. So you say, here's what I think, tell me what I should think next. Now, given what I'm thinking now, what should I think next? And so you sort of just iterate that process to refine your thinking. But then you also have a loop where you go, I'm going to think for a while, then I'm going to generate an answer, And then I'm going to go back, and now that I've got this sort of refined answer, I'm going to go back and think some more, right? Like, here's what I think might be the answer. Let me sort of think about it a little bit more, refine my answer. And it turns out that doing that has these remarkable benefits. And this is my last slide. So they have this network that has 7 million parameters. And, kind of compare that with the number of parameters in Gemini, DeepSeek, and O3 Mini. And it does better than those models do using 0.01%. That's 3 orders of magnitude less compute that's required. So you have taken something and reduced the compute you need by a factor of 1,000, and you're doing better than these general purpose models. And so I think the cool thing here is that, I think as a company, we're trying to move away from sort of very bespoke solutions and try and make things more repeatable. But there are technologies out there that can allow us to build very, very powerful models with a tiny fraction of the compute. And so we need to be thinking about in what cases is just a standard out-of-the-box language model appropriate, and we're just going to do prompt engineering on it, versus we might have enough data to learn this remarkably powerful model that's fine-tuned for the user's problem, and we can do that in a very efficient way.